carry on with a second talk, also from FU Berlin, and also in the same general area, but now using Gaussian mixture modeling for spectral identification.
Okay, thank you, Andrew and Eric. Okay, give me an opportunity to give you a talk about one of my recent works in so nice place. Okay, so and thank Marco and thank Erico that give a very good background introduction about the spectra of the stochastic process. So I don't need to take a lot of time to introduce the background again, I think. But I need to say something about just some notations. Firstly, so I assume that I have a macro chain. So here I assume it is in the continuous space, but discrete time. And of course, the dynamics of the macro chain can be expressed by okay, so a propagator, so P, like this one. So this propagator, it is in fact a integral operator, and the kernel of the integral of the operator is the transition probability. So here we can see that if Ux, it is a probability density at time t, then Pu is a probability density at time t plus tau. So tau is the lag time. And if we further assume that this macro chain is ergodic and reversible, then we can prove that so this operator, it is a self-adjoint operator, and it has only one eigenvalue is equal to 1, and then we can decompose this operator like this one. So it is a decomposition. So here lambda I, it means the i's largest magnitude eigenvalue, and Li is the corresponding eigenfunction. So it is the definition of the inner product. We should say that this spectral decomposition is very important. Here I just show you a very simple example. So here we consider a diffusion process in one-dimensional space, and it contains 4 potential wells, and it is the corresponding transition probability density. Okay, and we can calculate the eigenfunctions and eigenvalues of this process. So it is eigenvalues, it is eigenfunctions, and we can see that after the first 4 eigenvalues, the fifth eigenvalue is very, very small, and the others are even smaller. So it can be ignored. And from the spectral components, we can get a lot of things. So firstly, of course, the first eigenvalue is 1, and the eigenfunction is just a stationary distribution. And of course, we can calculate the ensemble average from the first eigenfunction. And secondly, we can also calculate the variable correlation functions. So the variable correlation function, it means, so if we define some signal at, it is equal to some function of the system at time t, and the bt equal to the other function. And then the correlation function, it can be defined by the expectation of at and the bt plus tau. So this value, on the one hand, it can be very easy to measure from the experiments. On the other hand, if we know the spectral components of the system, it is also very easy to compute from the dynamic model. So then it is a bridge between the simulation model and the experiment. And so in theory, we call it the dynamic fingerprints. So we can use it to evaluate if a model can match the experiment. And then another thing is that metastable decomposition, as Marco has said, so I will not repeat it again. And of course, the decomposition itself is provide us a low-dimensional approximation. For example, for the previous example, we only remain the first 4 components and discard the others. Then we can get a very good approximation with only dimension 4. And last, so it can be used to the determination of reaction coordinates because it has a very great feature that, for example, in this case, if this eigenvalue it is exactly 0, then I use these functions to compute the coordinate of the system, then the reduced dimensional system, it is exactly a Markov system. So it is a very good coordinate to describe the dynamics of the system. So now we know that they are very important. But the problem is that in most practical cases, we cannot calculate the eigenvalue equation directly because maybe it's very complicated. And what we can do now is only to estimate the eigenvalues and eigenfunctions from some from some observed trajectory. So the problem is that if we have some trajectory in a state space, then how to estimate the eigenvalues and eigenfunctions? Of course, the most commonly used and the most successful method is also the Markov state model. So Eric and Marco have seen a lot of things. So we just discretization, we divide it into a lot of beings. So in fact, it is some specific finite element method. So we get some small beings, and then we calculate the transition matrix on the beings. And then we can calculate the eigenvalue and eigenvector of P. And from that, we can get some estimate about the spectral components of the original system. But there are some disadvantages. The first one, it is very easy to see that the major difficulty is that how to select a good discretization. So in low dimensional cases, it may be easier. But in high dimensional, it is very difficult. And on the one hand, if the discretization is too cost, then the Markovian assumption does not hold. But if we cut it too finely, then we will meet the problem of the curse of dimensionality. Okay, so because we have no enough observed data to estimate the transition probability. And of course, the Markov theory told us if we know the eigenfunctions, then maybe we can design a very good discretization without so many beings. But the problem is that now what we want to know is the eigenfunction itself. So we cannot use eigenfunction itself to design the discretization here. And the next problem is that, of course, because in Markov state model, we only use some step function to approximate the eigenfunction, so it's just a very, how to say, non-smooth result. Another approach is called the variation approach. So it is proposed recently. So here it make an assumption that the eigenfunction L, it can be expressed by a linear combination of some basis functions. And this basis function can be arbitrary. If this assumption holds, then we can use the variational problem. We can solve this problem to get the optimal combination of the linear combination coefficients. We can see that if this assumption is true, that the eigenfunction belongs to the space expanded by the basis functions, then we can get exactly the eigenfunctions and eigenvalues from this problem. If it's beyond the space, then maybe we can also get some approximation. And I should say that here the matrix H1 and H0, both of them can be obtained from the experimental data, so they can be consistently estimated. The advantage is that we can see that the variational approach it is in fact a generalization of the Markov state model, because it in fact use some smooth function to use some smooth function instead of the step functions. So it give me more flexibility, and of course it can provide a smooth estimation. But the problem is that the same, in fact, the choice of basic function, how to choose it, I don't know. There is no semantic algorithm can do so, and here we can only try and see according to our experience. And secondly is that it is difficult to analyze the influence of statistical noise because we only know some trajectory. So how to evaluate the influence of the static noise content in the trajectory? We don't know how to do it in the framework of the variational approach. So based on the above discussed, I want to develop a new method to solve this problem. So it's based on in the Bayesian framework. So here we have some observed trajectory, and I want to use some parametric model to fit the dynamics underlying this trajectory. So, for example, some parametric model M, and then we can sampling the parameters according to a posterior distribution. And then for each sample of the model, then we can calculate the corresponding eigenvalue and eigenfunction. And then we can get an example of the eigenvalues and eigenfunctions. And then we can get anything we are interested in about the two values. And we can see that in this approach, the kernel thing is that how to choose a parametric model. And roughly speaking, an ideal model should satisfy these three conditions. The firstly is that, of course, it should be flexible enough to fit our unknown model. And the second thing is that, so the parameters, it can be, I mean, the Bayesian inference, the Bayesian sampling, it can be efficiently performed based on this model. And the third thing is that for a given model, for a given parameter of the model, it is easy to calculate the eigenvalues and eigenfunctions from that. So based on these three conditions, let's try some different choices. The first one is the transition probability-based model. So that means if we can, we wonder that if we can use some parametric model to approximate the transition probability density itself. I tried this one, and this is an example, but maybe you can use some other examples. So I assume that here it is a diffusion process, and I use a nonlinear diffusion process with some unknown parameters to approximate the dynamics. So I found that, so here the parameters, the sampling of parameters, it is feasible, but the problem is that for a given parameter, how to calculate the eigenvalue and the eigenfunction of this system, it is very, very difficult, except some extremely simple case. So generally, we cannot get an analytic result about the eigenvalues and eigenfunctions of such a system. So it cannot work. Another choice, sorry.
What was new?
Just some basis function.
Okay. Fixed.
It can be fixed or it can be changed, but both of them is very difficult to get the eigenvalue. I think only the case that the mu is a constant, and then we have only one m equal to 1, and so it is a linear system, then we can calculate. But just in this case, we have some methods. Another choice is that the correlation density. So here we define the correlation here. So Cxy it is equal to this one. So it is a joint distribution at tan t and tan t plus tau. Some researchers, such as Christoph Schulte, has do something about this one, because we can see that if we consider this, it is in fact a probability density distribution, so it can be consistently estimated. But so here, if we can, so here I try to use a Gaussian mixture model to estimate this one. Okay, so the result is that the sampling of the posterior distribution, it is feasible, but it is too time consuming, because here I need to calculate the likelihood of the model, and at each time when I want to calculate the likelihood, I need to scan all the trajectory, so it is very time consuming. And the next problem is that it is a little better than the previous one, because it is possible for us to calculate the eigenvalues and eigenfunctions from this model, but it involves some intractable multidimensional integrals. So we also need some numerical method to do this. So it is not so satisfied as choice. And another thing I should mention is that maybe it is not so obvious if we can estimate the correlation density Cxy. This one, if it so the approximate value, if it converges to the true value, it does not mean that the eigenvalue and the eigenfunction will also converge to the true value. I can construct some counter example to see this. So maybe it does not happen in the actual cases, but we should keep it in mind, because it means it is not a stable estimator.
In your counterexample, what kind of convergence of the correlation function do you have?
Correlation density means.
No, I know what it means. What kind of convergence? Does you have strong convergence?
I mean, so this converges to 0. If this converges to 0, it does not mean this converges to 0.
What's a sufficient condition for the correlation function to ensure that?
Sorry?
What's a sufficient condition on the correlation function convergence to ensure convergence of the...
I don't know, but I can show you how to construct the counterexample. In fact, it's very easy. For example, if we know Cxy, it is a true value, and we approximate by C hat, here, 1 minus epsilon Cxy plus epsilon. So here, some delta xy. So maybe not delta, but some Gaussian distribution, but a very, very small covariance. So it is, if epsilon is very small, then it is a very good approximator according to this norm. But it means that, okay, I mean, so maybe some x0. In x0, it is a very large self-transition probability. Then it will lead to a very large eigenvalue. But in fact, this eigenvalue is meaningless.
But if delta is actually smooth...
so maybe some Gaussian distribution. There's some Gaussian distribution, but the covariance is very, very small. Yeah, so then this part will give us a very large eigenvalue, but this eigenvalue is meaningless.
Still, I think that as epsilon goes to 0, the eigenfunctions and eigenvalues...
I mean, because it can be converged to 0 faster than this one, then that's it. So
after you get C, so the eigenvalues and eigenfunctions, we talk about that these for C, or?
I mean, even we can get a very accurate estimate of C. It does not mean that we can get an accurate estimate of lambda and L and eigenfunctions.
Yeah, but I mean, the question I have is just that what is this eigenfunction? The eigenfunction of C or of some
eigenfunction of the propagator of the P of the transition probability.
How is that related to C?
Sorry?
How do you get P from this C?
Oh, okay, sorry. Maybe I should. So here, P, maybe FF. So because for F, so fxy y equal to P xt plus tau equal to maybe z. Sorry, y conditional on zt equals to x. So it's a transition probability. And the Cxy, it is a joint distribution. P, so zt equal to x, and the joint distribution of zt plus tau. This one. So that means even we can estimate it very accurately, we cannot. So we cannot sure that we can get the estimated result of this one. So it's maybe a little surprising. For me, it is.
So you mean the operator norm convergence of C doesn't imply the operator norm convergence of P?
Yes. Yeah, of course. They are different. Maybe I can continue.
Yeah, please.
Okay. Okay, so the last choice, it is a non-trivial choice. So I introduce some new concept. I call it half-weighted density, but of course in many other researchers we can meet the similar one. So the relationship between the half-weighted density Sxy and Fxy and Cxy, it can be right like this one. So here it is y and the transition probability density like this one. So we times some factor here. Pi means the stationary distribution. And the relationship between C and S, it can be written like this one. So it's hard to say is there any physical meaning of S, but it is very useful. I will show you later. So, and of course, according to the half-weighted density, I can define the half-weighted operator. Okay. So the first thing is that we can show that the eigenvalue of S and the eigenvalue of P, they are the same. They share the same eigenvalue set. And the second thing is that their eigenfunctions has a very simple relationship. That means if we know the eigenfunction of S, then we can simply know the eigenfunction of P. And next thing is that as it is some local function, so local means if x, y tends to 0, tends to infinite, then the value of s will also tend to 0. And another thing is that with some technical assumption, we can prove that the integral of the s over all the whole space, it is finite. So we can use some local model to approximate s. For example, we can also use Gaussian mixture model to do this one. The difference between s and c, the difference is here, because the eigenfunction, eigenvalue of s is exactly the same of p. So if we can estimate s accurately, then we can get an accurate estimate of the eigenvalue and the eigenfunction. So I think it is an advantage of the half-weighted density. And of course here, we can prove that if we use the Gaussian mixture model to estimate the half-weighted density, then we can analytically calculate the eigenvalue and eigenfunction. So here it is, this matrix, it can be analytically computed, and from this one we can get everything. And another hand is about the posterior distribution. We can see that we can rewrite the posterior distribution of the model of the half-weighted density like this one. It's very interesting because here if we ignore this term, we only consider this term. What does this term mean? This term means that if we consider transition pair zt minus 1 zt, it is just a lot of independent data. Then this part is just the likelihood of the traditional Gaussian mixture model. And then all the linear algorithms such as Bayes method or maximum EM algorithm, both of them can be applied to here, and we can efficiently to sample the parameters of the Gaussian mixture model. So based on analysis, we use this model to solve the problem of spectral estimation. And because here I use a Gaussian mixture model to approximate a dynamic system instead of a static distribution, so here I call it a Gaussian mixture transition model, because I use it to approximate the transition dynamics. And it is very interesting to see the GMTM and relationship between the GMTM and the MSM, so microstate model. And we can see that if we choose we do not use the mixture of Gaussian distribution, but use a mixture of some step functions, then in fact we can get a microstate model. And so here the Bayesian estimate of the microstate model, it is in fact the Bayesian estimate of the GMTM. They are, so in principle they are same, just the difference of the different choice of the basis functions. And we can see that the estimation result of the GMTM and the variational approach, they are also very similar. So both of them is some linear combination of some basis functions. But the difference is here, the basis function of the GMTM, it can be updated or adjusted by sampling according to the likelihood function automatically. So we don't need to choose it by ourselves. So the parameters of all the basis functions, it can be adjusted. Okay, and an important thing is that, of course, within the Bayesian framework, all the uncertainties, it can be evaluated based on the samples. Okay, so just a very simple example. Firstly, it is a two-well potential diffusion process in one dimension. And okay, so here we know, so here I use the implied time scale as Marco has said, so it is independent of the sample time tau. And here I use two models. One is GMTM with m equal to 5, so only 5 components. And I use time-state microstate model. And we can see that, okay, so even with very smaller number of the basis functions, then GMTM can also get a much better estimation result. So it is estimation error of the eigenfunction. We can see that the GMTM is performs much better. It is not surprising because it is a smooth function. And here in MSM, we can only use some step function to estimate the eigenfunction. So that's a histogram example. Okay, so we can see that. Yes, the eigenfunctions. So we can see that it is a Marx model. It uses some step functions, and here the red line we use some smooth function. We can see that it approximates very well. And okay, I also use alanine dipeptide example, and we know that I think most of the people know this very well. So it is a very simple peptide, dipeptide, and the dynamics of the system can be well described by these two angles. And okay, so here I use some different, maybe not so clear. Okay, I use a GNTM with 6 Gaussian components, and the Marx model with 6 states, Marx model with 12 states, and the Marx model with 18 states. We can see that the GMTM with 6 basis functions achieve the similar estimation accuracy of the Marx state model with 18 states. So it means it is a very accurate and a very economical way to do the estimation of the spectral components. And similar is about the third implied time scale. And it is the first eigenfunction estimation result, and it is the GNTM result by using the Bayes method. It is by using the maximum likelihood, and it is we can see that they achieve the similar estimation result. The second one and the third one. Okay, so just a conclusion and future works. And from this research, I think the one of thing is that we can see that the half-weighted density or half-weighted operator, it is a very important tool for us for the spectral analysis. And the future works, including that, firstly, of course, the more efficient sampling algorithms or maximum likelihood optimization algorithm. And in fact, here, a very important problem is how to choose the number of the Gaussian components. Here, I don't know how to do it. So maybe we can do it in some non-parametric estimation way. So maybe we can do that. So thank you.
Thank you. Questions? I have a question about if your truth is within the class of basis functions that you are using.
Mm-hmm.
Do you have a consistency result that says that if you take a long enough piece of data, you will get the right estimates of the weights?
In fact, I have not, but I think if we want to do so, we need to assume that, yeah, of course, the underlying dynamics is exactly can be estimated by some Gaussian mixture model, right?
Yes, so but assume you're in that class.
Yeah.
And then ask. Otherwise, you'd have to go to the non-parametric version of it.
I think maybe we can do, because it is very similar with the traditional Gaussian mixture model.
Mm-hmm.
And I think maybe we can get some parallel result with that.
I think that would be a good result to have to justify the method.
Yeah, of course.
Other questions?
Just to get this right, the fact that you choose this Gaussian mixture model
Yes.
Does not in any way restrict sort of the class of transfer operators that you consider?
Sorry?
It does not restrict in any way the class of transfer operators from which you try to estimate the eigenfunctions? It's completely general?
I think it depends on, because the Gaussian mixture model itself is a very general approximator, and on the other hand is that I can prove that in some assumption, but a very technical assumption. For example, all the the sum of all the eigenvalues of the propagator is finite. So some assumptions like that. I can prove that the integral of the S, so the half-weighted density, it is finite. So then it can be approximated by some density. If Gaussian mixture model, it is a general estimator for densities, of course for smooth densities, then it is also a general approximator here.
Provided you have sufficiently many.
Yeah, of course, sufficient many. Yeah, sure. So that's the problem why I need to choose the number of M. It is still an open problem.
So you want it to be a compact operator, so that you can do some kind of
Yeah, of course. Yeah, it must be compact. Sure. I think the nucleus, so I mean the sum of all the eigenvalues is finite. It is stronger than the compact.
It is, yeah.
Yes.
It's 12.
Yes.
That actually means it could be a covariance operator.
Yeah.
Other questions? Okay, thanks very much, Hao.
Thank you.